everyone. Today we're going to talk about table data instructions within the Omron CP1H PLC. And what table data instructions really are is a group of consecutive data that we manipulate in some way or another. So here on my screen you'll see I have my set stack, push to stack, first in first out, last in first out, my dimension tables where I can use my set record location or get record location. I have data search, swap bytes, min, max, sums, checksums, and then we go back to the stack and we look at the stack number output, the stack data read, stack data overwrite, and then the insert and delete. So let's look at those instructions within this Omron CP1H controller. Now the first instruction is actually a set stack, and what the set stack will do is set up my group of or my consecutive data areas in my PLC. And what you'll see is you'll see the first one is my PLC address of my last word in a stack, and so the first two there represent the last word in the stack. The next two represent the stack pointer and where the pointer is. So because we use the first three words as addresses, locations, then the actual stack starts at the table plus 4. So let's look at the if we look at the actual PLC memory addresses. So there's your M, your memory address, and it goes to all the way down to here. So the first three are actually your pointers, and then you have your stack that actually begins at address 4 right here. So here's my instruction, and you can see we're communicating to the PLC, we're talking, and we're monitoring here. So what we've done is we've said let's start a stack, and that's the data memory 0, which is right here, and the number of words that we want in that stack is 10. So what we'll do is we'll energize this stack. So we'll turn that on, and when we do, what happens is my stack actually becomes initialized. And what that means is that everything now is available for other things to do, like push to stack and etc. So there's a lot of other instructions to deal with that will deal with the same stack that we just set here. And typically you want to do this once in your program, typically near the start or the start flag. So what we'll do is I'm just going to turn that off now. So now we have our stack set. My last address is actually F, so 15 words are in the stack. The pointer is actually here at data memory 2, which is point 4. So my first word that I'm going to be looking at is data memory 4. So if we look at our next instruction, which is going to be push to stack, and what the push to stack will do is actually input wherever the pointer is a word, and then what it will do is it increment that pointer in the stack by 1. So in our case here, our push to stack, what we're going to take is our table location is data memory 0, which is our stack location, and then we're going to take a source word of data memory 20 and we're going to put it into that stack. So let's change this value in data memory 20, and we'll change it to the number 1, 2, 3, 4. Now we have 1, 2, 3, 4. So now let's push that onto the stack. So we'll energize this instruction. And when we do, what you'll see now is that data memory 4 in our table below has 1, 2, 3, 4. And you'll also notice that our pointer is now pointing at data memory 5, which is the next one down. So it's actually put the data in and then increment the pointer. Now let's try that again. Let's change this value now to, say, the number 1111. And what we will do is now energize this bit again. And when we do, now we have 1111 in data memory 5, and our pointer again has changed to 6. So let's do one more, and we'll set this to a value, we'll say, of 2222, and energize this again. And when we do, we have the value 2222 in there, and now my pointer's set for 7. So what I'm doing is as I add each value, it's just incrementing down on the stack. Right, we'll just reset that input bit. Now, the next instruction is my first in, first out instruction, or FIFO instruction, they call it. And what that will do is the first piece of information in actually will come out of the stack. So here, it's the oldest data. So in our case here, the one in data memory 4 will come out of their stack, and then the stack pointer then decrements by 1. So let's see that in action. So our oldest piece of memory is going to be the first one we put in, which was 1, 2, 3, 4, and that should actually then go to data memory 20, which is my destination. So let's try that. Set that on, and sure enough, that's exactly what happened. You'll see that 1, 2, 3, 4 came out of my stack at data memory 4. My counter then decremented by 1, so now it's 6. So let's set that off. And now if we want, if we go back here, let's push that back onto the stack. And it puts it back in, but now at the new location, which is data memory 6, and then increments the stack by 7 because we used the push again. So that's first in, first out. The other opposite of that is going to be last in, first out, and the last one we put in was just this 1, 2, 3, 4. So what it will do is it takes the stack pointer, it takes the last one, and then the pointer gets decremented by 1. So it removes that last one, then decrements the pointer. Now that data is not erased, it's just left unchanged, but the pointer now points to the location which will erase that. So let's just take a look at that, and what we're doing is we're going to do a last in, first out, and then we're going to output that information to the destination word data memory 21. So let's turn that on, and what you'll see is 1, 2, 3, 4 then appears, and in our case here, our pointer now goes to 6. Now the pointer go to 6, which is exact same as the location in which we just removed that information from. Okay, so that's the stack and setting it last in, first out, first in, first out, and our push to actually load up the stack. We'll turn that off. Now our next instruction that we're going to be looking at is actually our dimensional table. And the dimension table record, it's used in the PLC to automatically put in a lot of values like pressures and temperatures and things like that for a certain process or recipe in your controller. What this will do is separate your records and allow you to read and write from those records using index registers within the controller. So the first thing we do, just like we did with the stack, is actually to dimension our record table. So use the dim. So what we'll do here is we'll turn this on. And when we do, and again, what we do is usually do that in a first scan or whenever we need a new dimensional table. And we have table number 1. We have the length of each record. We said it's going to be 3 words long. And the number of records, we're going to say there's 10 records. So we're actually looking at 30 registers that we're looking at right now on this dimensional table. And then from the dimensional table, what we do is we can write the PLC at a memory address of the first word of the record to the index register D. So basically what it does is says, okay, I'm looking at table number 1, my first record here, and I'm going to put it in my destination index record, which is IR0, or what I deemed as IR0. So when I turn this on, what it will do is it puts it in IR0. Now remember, index registers, you cannot see them until you use them. So in order to use them, we use the next instruction, which is the get register. So what it will do is it will writes the record number of the record that includes the PLC memory address to M to D. So what this means is that it takes the data memory 1, it takes the index register wherever it is, and then puts that as a value in data memory 200 in our case, so that we can see exactly what record we're pointing to. So we set that on, and it points to 1, which is exactly what we set in the first one. So that's dimension. Very useful instruction. The next one that we're going to take a look at is data searching. In data searching, we'll use a control word, and a control word tells you how many words are in the range, and also what happens when the output matches and the output number of matches. You can set that in the second control word. So in our case here, we're doing a search. Data memory 300 is our control word, so let's just roll down here to 300. There we go. And we're going to search for 100 words, and we're looking for, and starting at data memory 0, and we're looking for the value 1234. Now what search will do is automatically set our IR channel, index register channel 0. And when we do that, it sets it to the first location which it finds it. In our case here, what we're going to do is then move that index register to data memory 302. So basically, again, we're going to search it from the start to the finish. It takes the first available match, sets the IR, the index register, and what we're going to do is take that move and take that index register and move it to our actual data memory. So we should actually see the value 1234 appear in 302 when we energize this. So let's go back up here. We'll set this on. And when we do, sure enough, that's exactly what happens. The index register found the first location of 1234 during our search. It then grabbed it and then put it into data memory 302. The next instruction is our byte swap. And byte swap is very useful when we're talking about communications and talking to different devices on our network that we may have. And a lot of the time, different controllers will handle a word, which is the 16 bits or 2 bytes, differently, and they'll send the right one as opposed to the left one first, or the left one as opposed to the right one first, and so the two pieces really don't want to talk to each other. So what we use is a byte swap in order to flip things around. So in our case here, this is what the instruction will do, and it sets the number of words. In our case here, we're going to have 2 words. We're going to go to the data memory 400 as the starting of the first word. So let's call it 400 here. And what we have is 1, 2, 3, 4, and we have 5, 6, 7, 8, the next one. So it's going to take those two and it's going to swap them. So when I do that, I should say 3, 4, 1, 2 and 7, 8, 5, 6. Let's see if that happens. And sure enough, that's exactly what happens. 3, 4, 1, 2 and 7, 8, 5, 6. Now, if I were to swap them back, turn that off, and then turn that on again, it should return to the original state. And yes, that's exactly what happens. And now I go back to 1, 2, 3, 4 and 5, 6, 7, 8. The next instruction is our max. So within a group or a table, we can actually find a maximum value located within that group. And again, it uses a control word, and we set the number of words in a range, and then we set the output. So we can output whether or not the index register is set as well to tell us where that max is, and either it's signed data or unsigned data. So in our case here, what we're going to do is it goes on 410. 410, we have the value of 100 in there, which is 64 hex. And so it's going to start at data memory 100, and it's going to read the next 100 registers and figure out what is the maximum value it finds in there, and puts in the destination location data memory 415. Let's turn that on. And the highest word or highest value that we have is 1111 hex. So that's find max. And just like find max, we have find min. So there's my find max. And find min works the exact same way. We set the number of words in a range, and what it will do is search those words, find the minimum value, and set it. We can also set the index register if we want to, in order to find the exact location of that minimum value. So in our case here, we have data memory 420, and our range again is the same, data memory 100. We're going to search 100 words, and we're going to put the minimum into data memory 425. So we'll turn that on, and right now 425 contains the value 999 or 9,999 hex. Let's just turn this on, and within those 100 words there is a location now with a value which is the minimum, which is 0. So it works very quickly, very accurately. We also have a sum. Now what the sum will do is actually sums all of the registers that you specify, and it will then output the result in 2 words. So again, we have control, and here's the number of words in the range. Then we specify whether it's signed or unsigned, whether it's binary or BCD. We have the words or bytes at the time, and if it's bytes, then we use either leftmost byte or the rightmost byte in order, and all the rest are 0. So in our case here, what we're doing is we're summing, and we're calculating 100 words, and they're in BCD. So we're taking 100 and we're calculating them out. So let's take a look and see what we get. Turn that on, and sure enough, it calculates it out. We have now a hex value representing the sum of those 100 words that we asked for. CHECKSUM is the next instruction, and the CHECKSUM, again, we use a control word, and again it tells us number of bytes or words in a range, and then it tells us the whether we're calculating on bytes or words, leftmost, rightmost, exactly like we did before. So what it will do is take all those values in the table, it calculates by using exclusive OR to all those different words, then it takes the result and converts it into an ASCII character. Now this is used for a lot of serial communications that we have, and what you'll notice is I'll put some references down in the links below that takes you to some of the host link data communications, which is serial communications to the Omron equipment, and that will actually use the CHECKSUM calculation in order to communicate and ensure that all the bits when you transmit and receive are received and transmitted equally on each end, and you don't lose any bits in between. So in our case here, we're calculating the CHECKSUM calculation on a series of information, and it gives us a result. We'll just turn that on, and when we do, we get a result here, which again is actually shows in hex, but it's actually in ASCII. 3034 is actually equal to a value of 0, and the 34 is 4. So 04 would be the CHECKSUM calculation that we have returned from this calculation here. Our stack size read. Now we go back to our original data, back up here on our stack that we initially set, and what it will do is it actually takes a look at the count and reads how many are in the stack right now. So if we turn this on, what you'll see is it says 2. So now what it's saying is that we have 2 records in the stack. So our current pointer is at 6, which is right here, and we said we start at 4, so we actually have this word and this word in the stack, which is 2, which is correct. The next instruction is the stack data read. And what the stack data read will do is it will reads the data without changing the stack pointer. So it just takes the value of what you want and pulls it out into another word, but it does not change stack pointer, so your stack remains exactly the way it was before. So in our case here, what we want is we want our first stack address, which is 0. We are read position, we'll say position number 2, and we're going to put it into data memory 510 as our result word. When I do that, let's set that on. And what we get is 1111. And 1111 is actually exactly where position 2 is, because right now it's on 6, and what we're doing is offsetting that by 2, 1, 2, and that's our location that we're getting right now. The next one is stack data overwrite. Now the stack data overwrite allows you to input data into your stack here without affecting the pointer. The pointer does not change, and we will then overwrite whatever's in the stack with the new data. In our case here, we're going to position number 2, we're going to put that 4321 into it. So let's turn that on. And you see 4321 now goes into that location. And our stack pointer does not change, it's still at 6. Now we have the next one is stack pointer insert. And what we're going to do is we're going to insert information within the stack. And in this case here, my offset and my pointer does change. So it will actually insert the data and change that stack pointer. So in here, what we're going to do is insert position number 1. We're going to insert 6, 7, 8, 9. So let's turn that on and see what happens. When we do, we can see 6, 7, 8, 9. Position number 1, which is exactly where the offset was to the pointer, which was at 6. And now you'll notice that's 7 now. So that's the stack inserter input. Now the stack data delete is the last instruction that we're going to take a look at. And basically what it will do is it deletes the record and then moves the stack pointer, decrements it by 1. So in our case here, we take our stack pointer, our record deleted position number 1, and our deleted data actually comes out of the stack and we'll put it in data memory 600. So let's turn that on. And sure enough, that's exactly what happens. Our position number 1 was 2222. You'll see that our pointer now goes back to 6. And there's our deleted data. And 6 is where the stack pointer is right now, which points to that last information on the stack. Okay. Now, if you like this video and like to see more, there are 3 ways in which you can help us out. You can give us a thumbs up so other people can find this information. You can subscribe to our YouTube channel at the end of the video, or you can go to accautomation.ca and subscribe to our website. Now on the website, you'll find all the links that we mentioned in this video. Also, when you subscribe to the website, you'll get notification every time we publish new content to the site. You'll also get 2 free ebooks on numbering systems and robust data logging. And the third thing to help us out is to tell a friend or colleague about the site. Alright, that's it for now. Thanks for watching.